looking at some of these examples of irrational functions, okay? So let's take a look, and we might ask, well, what is that graph, okay? So here's the graph, okay? We should know and realize what 1 over x squared looks like, okay? That was addressed in the previous videos. There's 1 over x squared, okay? Now, um, this is a translation. It's been flipped over. It's been flipped over the x-axis, hence why it's opening downward. And it's been shifted down 3, hence the horizontal asymptote at -3. So, as we can see, that just accounts for it. That is going to give us a y-intercept that we didn't have previously. And so here are the things we said about the asymptotes. Okay. Here's another rational function. If we're looking for the horizontal asymptote, vertical asymptotes, the x and the y-intercepts, in this form we can see immediately that the horizontal asymptote is going to be y equals 1. That should be y equals 1, not y equals 0. Okay. When factored, the denominator factors easily, giving us two x-intercepts of 1 and -1. I'm sorry, two vertical asymptotes of 1 and -1. Um, when factored above, when this expression is factored, okay, it will reveal us the two x-intercepts, and the y-intercept is obvious in this. Okay, the graph, right? Um, what's going to happen with this graph? Our vertical asymptotes are going to occur here at 1 and -1. Okay. Our x-intercepts are occurring here at 2 and out here at -6. So this thing is going to cross over at -6 and then come up and come to rest on the bottom side of the line y equals 1. So with two vertical asymptotes, we have 3 distinct regions. Sorry. We have the region in between the two asymptotes and the regions left and right of those asymptotes, okay? If need be, draw up a sign table to assure yourself of what that graph is going to look like. We're going through 12 on the y-axis, okay? And we can't come back down because then we would cross over here at the with another x-intercept, but we have already spent our x-intercepts. There's some rationale behind that. Okay, here, taking a look at this rational function, ratio of the highest powers top and bottom is 1, so therefore y equals 1 is the horizontal asymptote. There is no value causing the denominator equal 0. There is no value causing the denominator equal to 0. So that means there's no vertical asymptote. That means that this function has no interruptions. It's defined for all values of x. Okay? It's kind of a unique rational function in that to that extent, in that um, there is no vertical asymptote. There is a horizontal asymptote for y equals 1. Factored, this reveals that we have 2 and -2 as our x-intercepts. And we got our y-intercept at -2. Okay? We're stating the function is symmetric about the y-axis. That's very obvious because of all the powers being even. It doesn't know the difference between a positive and a negative, so therefore it's very symmetric about the y-axis. As stated, the horizontal asymptote is 1, y equals 1. As stated, there's no vertical asymptotes. When factored, we get the x-intercepts and we got the y-intercept. Here comes our graph. Okay, very pretty graph. Y-intercept, x-intercept, horizontal asymptote at y equals 1. No interruption in the flow because there's no x values for which it cannot take on. Nice symmetrical graph, as we can see. Okay, a kind of atypical horizontal, an atypical rational function without any vertical asymptotes, but that's what it is. Okay. Okay, here's a rational function. Horizontal asymptote, ratio of the highest power terms. X over x squared becomes 1 over x. And that means it's going to behave like 1 over x in the long run, which means it's going to be heading for the x-axis, the line y equals 0. Okay, so we got the x-axis acting as our horizontal asymptote. This, of course, will factor what x minus 3, x plus 2, giving us intercepts at -2 and +3. And a y-intercept at -1, 6, and an x-intercept at -1. Okay, so here we are factored. Again, in this form, or whenever we got a higher power in the denominator, it's always going to head for the horizontal line y equals 0, or the x-axis. Whenever the higher power is in the bottom, that's what's going to happen. Okay, so that's been accounted for. Then we got the horizontal asymptote of y equals 0. When factored, we get the vertical asymptotes -3 and 2. Okay, we sketch the thing in. Okay, here's our vertical asymptotes, -3. Oops, sorry, -3, 2. All right, here's our x-intercept at 1, negative, and 1/6. Again, if you're not confident with where the graph goes, when we do it, we sketch in the horizontal and vertical asymptotes, so they're guidelines for where the function is headed. So, and of course, if all else fails, then you can always draw up a sine table on this, and it will tell you whether you're above or below the axes. But there's our graph. Okay, here's another one. Ratio of the highest powers, top and bottom, is 2, so our horizontal asymptote is y equals 2. This is going to factor, as you can see. We pulled out a 2, and then we have a factor of x plus 1, quantity squared. In a polynomial, that results in a multiplicity. As a multiplicity, you know what that implies. It implies that it just touches that point at -1 and then rebounds off of it. We're going to see that will also be the case with these rational functions. So that x-intercept is going to be of a multiplicity as stated here. Okay, we're going to have the y-intercept at -1/6. We have x-intercepts at 6 and -2. Okay, so let's see if that is featured in this graph. Okay, here we are. Our vertical asymptotes at -2 and +6. Okay, our horizontal asymptote at y equals 1. All right, our x-intercept here at -1, our y-intercept at -1/6, and the multiplicity happening right there, sending it right back down. It's not going to drop off vertically, okay, because then it wouldn't be a function, but it's moving towards that, ever getting closer and closer and closer. Okay, again, if you did a sine table would validate for you in what regions to graph. The asymptotes would tell you where to move, and the intercepts would tell you through what points to go. Okay. Okay, here's another one. Our ratio of the highest powers top and bottom is 2x over x squared. So that's going to behave like 1 over x. Again, it's bottom heavy. Bottom heavy meaning higher power in the denominator. Going to behave like 1 over x in the long run. So our horizontal asymptote is approaching 0. Okay. As I say here, the unbehavior is determined by the ratio of highest powers between the numerator and denominator, which here says it's going to behave like 1 over x. Okay. All right. And so there's a little refresher on that. Now, more specifically, I said it was going to behave like negative 1 over x, which this is the behavior, which means, I guess, it looks like it's approaching 0 from the bottom side, moving towards positive infinity, from the top side, moving towards negative infinity. Okay? We definitely see that this factor is in the denominator, which offers us intercepts at 3 and, asymptotes at 3 and 4. This is with factor into x minus 4, x minus 3. So we've got our vertical asymptotes at 3 and 4. If x is 0, y is 0, so we get the origin as our single intercept. I make a statement here that says the sign table might be warranted, particularly in determining which occurs in between the vertical asymptotes. So again, 2 vertical asymptotes leaves us with 3 regions, okay? And without only knowing this idea that we're approaching it probably from the underside and moving towards positive infinity, and from the top side of the asymptote moving towards negative infinity, we'll want to see that, okay? So I've illustrated right here, because this was kind of a little hard to break up, so I kind of put it in pieces. So let's see what's happening here. Okay. All right. So this is a little segmented. Okay. So in between the asymptotes, we've got this kind of region. Okay. Um, we said that we're going through. Okay. So what is happening here is this. Okay. Here's the graph. Okay. Here's my asymptotes. If you recall, just come back. The asymptotes are at 3 and 4. Okay. So here's x equals 3. Here's x equals 4. In between 3 and 4, okay, we are within this region here. Kind of, it's not parabolic, okay, because parabolic is never confined within vertical lines as this is, okay. We said moving towards positive infinity, we expect that we're going to be riding it from the lower side of the horizontal asymptote of y equals 0, or the x-axis. And then we kind of surmise we're going to ride it from the top side. Okay, so what I did is over here, I showed you, here's this portion of the graph here, going through the origin. Okay, so it's going through the origin, but then it's coming up, it's going to reach some point where it's going to dip back down and start heading towards the horizontal asymptote. So it had to go through here, and then it had to come loop back down and kind of settle in on the top side of that horizontal asymptote. So again, a sign table would help to illustrate those things a little bit more clearly for you. Here's another one for us to look at, okay? Obviously, we're going to go towards y equals 0 is our horizontal asymptote, okay? Again, rational functions at the highest power of x in the denominator. The end behavior will always move towards the horizontal line, x equals 0, okay? Other than that, we've got x-intercept easily found at 5/3 positive, y-intercept at 5/6, factorable in the denominator, revealing our asymptotes. There's a factor into x plus 6, x plus x, but x plus 6, x minus 1, right? Okay, so we get asymptotes at -6 and +1. There you go, -6 and +1. There's our asymptotes there. Okay, we've got a single intercept, a single x-intercept at 5/3, it's just here, okay? And we've got this y-intercept at 5/6, all right? So our asymptotes are here, okay? And come again, all right? Our asymptotes are here and here. Again, a sine table might do you justice, and determine whether the region's above or below that, okay? But you can see we had to go through this, but then we're coming to rest on the top side of it over here, okay? Takes practice, okay? This will be the topic for the last of the rational functions where we have what we call slant asymptotes, but that'll do it first for now.